Ça me fait plaisir d'accueillir Casey Kennington ici à Montréal. Il est à Idaho et son université qui s'appelle Boise, ça provient du mot froid. C'est une université. Was it actually a French-speaking university at any point?
No, it's always been English-speaking.
Et puis, voilà. Il est professeur agrégé au département d'informatique de la Boise State University, où il mène des recherches sur les systèmes de dialogue vocal sur les plateformes incarnées, embodied. Son objectif de recherche est de comprendre ce que signifie pour les humains de comprendre, représenter et produire un langage, une langue. Son prix career de la Fondation nationale de sciences des États-Unis se concentre très sur l'enregistrement de petits modèles de langage avec des informations multimodales, c'est-à-dire toutes les modalités sensorielles telles que la vision, qui est une modalité sensorielle, et l'émotion. You said emotion there. I'll be curious to see how you see emotion as a modality, telle que la vision, pour l'apprentissage interactif. Maintenant, les grands modèles LLM ont principalement été formés à l'aide de grandes quantités de textes, mais des progrès notables ont également été réalisés dans l'intégration de la vision et d'autres informations sensorielles dans les LLM. Cela signifie-t-il que les LLM sont prêts pour devenir les agents incarnés, tels que les robots? C'est ça la question de Casey. Il est le plus proche du cœur de toute l'année, cette année, même une école d'été qui va suivre. Bien qu'il y ait eu des progrès importants, les défis techniques et théoriques subsistent, notamment l'utilisation de modèles de langage non ouverts comme ChatGPT et OpenAI. OpenAI n'est pas très open. Les exigences de taille du modèle, les exigences de taille des données, les exigences de vitesse, la représentation du monde physique et la mise à jour du modèle avec des informations sur le monde en temps réel. Dans cet exposé, M. Kennington expliquera les avancées récentes dans l'intégration des LLM dans les plateformes robotiques, les défis et les opportunités pour les travaux futurs. And with that, I hand over to Casey Kennington. Welcome to Montreal, to snowy Montreal, as you'll see behind me.
That's amazing. Well, I hope people were able to make it through the snow. Can you see my slides?
Yes, they're fine.
Great. Well, thank you. It's great to be back, and it's been a great series so far. I've managed to listen to all the talks, at least most of them, most of the way through up until now, and it's been a really interesting and informative series. My talk is about robotic grounding and LLMs, advancements and challenges. The first question, of course, is if grounding is in the title, then someone might ask me this question: what do I mean by grounding? And I will give you answers throughout. There are some papers I will review that claim to do grounding, and I will explain what I think they mean, and then I will explain what I mean when I talk about grounding in the research that I do. The first part of my talk, there are three parts. This first part is I want to introduce why we would use large language models with robots, and also look at the literature on vision language transformers. Recently, Zhen Yugan, a Syracuse University mechanical and aerospace engineering professor, believes integrating robotics and generative AI will revolutionize various industries by providing more intelligent, adaptable, and efficient robotic systems. We can expect over the next 5 years to see a new generation of robots that are capable of making complex decisions and operating with a higher degree of autonomy. This will be particularly important for applications such as autonomous vehicles, drones, and legged robots that require real-time decision-making in dynamic environments. So this is one person talking. There are many people who think something like this, that robots are going to be much more integrated in work, in domestic settings, and the list goes on. And the promise of large language models is really opening a lot of imagination here. So the first question I would like to look at is, why would we use large language models with robots? The first is, humans anthropomorphize robots and often expect them to be able to speak well. If a robot has a mouth, the expectation is that it can speak. If the robot has eyes, the expectation is that it can see. And people will go up to a robot and interact with it with those expectations. People will even look at a Roomba, you know, a vacuum, an automated vacuum cleaner that looks no more than a giant puck, and they will anthropomorphize it for certain things. Also, roboticists don't like to deal with language, and large language models seem to handle a lot of language phenomena. I've been to a lot of conferences with roboticists, and they avoid language as much as possible because they know that it's not just something that you attach to a robot and get working. It takes a lot more effort than that. But language models, those are way better and way more powerful, and they seem to have more promise. Language models are very good at classifying and generating sequential data, which robots, of course, need and do a lot on their own. And we'll see some examples of that in a moment. More recent large language models aren't only trained on text, they are also trained on text and pictures. And that is important because robots need to perceive and act in the world around them. So to move towards the multimodal language models, a student in my research group, Clayton Fields, a PhD candidate in our PhD program, recently did a literature review on what are called vision language transformers. Vision language transformers are large language models that incorporate vision into them, usually through pictures, sometimes through video. And in order to do that, they have to represent the visual world somehow. And they do that in three different ways: region features, patch embeddings, or grid features. And I won't go into too much depth into these other than to point out that the difference does kind of matter. The decision of how to represent the visual world affects the model. So for example, here is a use of region features. It's basically going to take the an object detector is going to put bounding boxes around objects and label them, and those labels themselves are part of the incorporation of vision. So it's not low-level features; it's at the symbolic level. Whereas patch embeddings are more at the low level, where they kind of treat an image as a grid, and all of those can be sort of flattened and put into some sort of a neural network, in this case, a transformer. And those are very different ways of representing the visual world. Some are more at the symbolic level, some are more at the low level, at vector representations, for example. And they're trained in similar ways. Sometimes they're trained together. Sometimes they, like text and image masking is used. A lot of these papers claim that they're doing grounding, and what I find is what they mean by that is that vision and language are used in the same model. And to most people, it doesn't really matter how text or language is represented. It doesn't really matter how vision is represented. As long as they're in the same model, somehow grounding is happening. This is a list of the papers that Clayton reviewed. There are about 30 of them, and you can see there's different feature types, different encoder types that follow from language models. And we had to kind of cut it off at about July, August this year, but there's a new one every week. Like, this is a very burgeoning and growing research area. These models, of course, are huge. It started with Vilbert, I would say, in 2019, and you can just see since then it's many new models every year. So that's the first part of my talk. The second part of my talk, I would like to survey a few papers that are out there that give a good representation of what language models are being used for on robots. Hopefully these represent a sample of different ways researchers and practitioners use them and showcase different task settings and needs of robots. The first paper isn't really using robots, but is related in an important way. It's called the Tool Former. You may recognize this paper. Someone who I've cited a lot, Luc Sedelmoyer, has done some stuff in the grounding world and in robotics as well. here's kind of what's going on. You give it a text, like the New England Journal of Medicine is a registered trademark of the Massachusetts Medical Society, the MMS. But in the text, it might just have MMS, and you might not know what that means. So how can you figure that out? Or this one, out of the 1,400 participants, 400, or 29%, passed the test. Well, how do you get from, what do you have to do to get from these two numbers to this number? That might be an important thing to know. Or then the name derives from la tortuga, the Spanish word for turtle. So you can kind of see there are different things that the text has in it, but you might be able to pull information out of this text and find tooling for it, what they call tooling. And in their case, a tool is a API call. So a question and answer system, you would call, who is the publisher of the New English Journal of Medicine? MMS. And now we know what Massachusetts Medical Society, and now we know what MMS stands for. Or out of the 1,400 participants, 400 or 29% passed the test. You would pass that information to a calculator API. 400 divided by 1,400 is 0.29, so 29%. And so you get the idea here. So it's a tool, but it's not like a tool like you might think a robot is acting and using, or that a human would use. It's a tool that you can pull out of text. But the reason why I bring this up is because these kind of API calls look a lot like just a standard function call, and that's often the way we control robots. There might be a function called move. So you can give it parameters to tell it to move forward, turn, or move backwards, or move an arm, or display a face, or speak, or something like that. So this isn't that far from that. Interesting research. Anyway, the next paper I'd like to show you is building cooperative embodied agents modularly with large language models. Modularly is an important word here. When we think of language models, often they are trained end to end, whether it's a question answer or machine translation. You have the inputs and the outputs, and the model learns everything in between. But with robots, they're usually built up of modules. So there might be an arm, there might be a head, or the wheels, or legs, and all of these different modules have different control units. And you have to treat them as modules, which means it's really difficult to train a large language model end to end with robot knowledge, or within the robot. So what these researchers did is they treated two large language models as separate modules. So they have kind of the agent, which is it can be a robot, it could be a virtual agent. And the agent is interacting with an environment, and other agents or people might be part of that environment. But they act in the environment, they observe the environment, and then they have a module of observation and belief. And belief is usually a distribution over different states that the environment is, what's happening in the environment, what's been observed. But then this information gets fed into two different large language models. One is the reasoning module, and one is a communication module. The communication module has some prompts, basically an instruction head, goal description, state description, action history, and it spits out a dialogue history. Or an action list, excuse me. This is all input, and it spits out an action list. The output is an action list. And the reasoning module, you give it an instruction head, state description, action history, goal description, dialogue history, which is very similar to what's happening here, but it also takes the input from this other communication module, and it answers, and it comes up with the answer extraction. So what it's going to say or what actions it's going to take. So here's two ways of using a language model within a robot. The way the information is passed through and represented is usually as tokens. The next one I'd like to show you is called Film. And this is work from Carnegie Mellon and Facebook AI. Jonathan Bisk is a name I recognize here. He does really interesting things with robots, large language models, and he's very interested in grounding. So the idea here is there's kind of two inputs that the robot can take. It can see its environment through a camera. In this case, it's showing as a virtual agent, but most robots are made virtually so that you can test a lot of its abilities virtually before you test it on the physical robot. So they have something like that here. And someone can give the robot an instruction. For example, drop a clean pan on the table. And at the moment, the robot is holding a pan, but it's a dirty pan. So what does the robot need to do? Well, you take the instruction, pass it through something like a language model, and that outputs subtasks. So you pick up a pan, put it in the sink basin, turn the faucet on, turn the faucet off, pick up the pan again, and then put it on the table. So there's this sequence of instructions that it has to go through, and it can get this sequence of instructions from a language model, these tuples. That gets put into the semantic search policy, and then there's a way of representing the visual world. In this case, you can have what they call a semantic map, and that just means that it has observed the world and has kind of labeled where things are and how it can navigate through a space, and then those things get joined together to determine what actual actions need to happen, and then it actually performs the actions. But what's interesting here is, like the last one, we have language in, tuples out that are useful to the robot. This one, physically grounded vision language models for robotic manipulation. This one claims to be physically grounded. And what they're doing here is a little bit different. So they have a model called the vision language model. They take an off-the-shelf vision language model like Vilbert, and they recognize that it doesn't have information in it that you might find in text. Like, you might know that a bottle is made of plastic, and you might know that this cup or this mug is made of ceramic, but you might not know that this is less fragile than this. So the relation, an important relation between them. And that's important because robots have to grab objects. And if it squeezes this too hard, it will shatter it. If it squeezes this too hard, it might crinkle it a little bit, but it's not a big deal. So you have a vision language model and a large language model. So these are both language models that are being used with robots. The robot might observe a scene like this, and someone says, bring me the ceramic cup. And it has to determine, okay, both of these, according to my object detector, are cups, but which one is ceramic? And it actually uses English. Is this cup made of ceramic? So it would take this cup, pass it to the vision language model, and ask, is this cup made of ceramic? That's actually something that it's been fine-tuned for these kinds of questions. And it answers yes or no. So it's not using some code or computer language. It's using plain English. Is this cup made of ceramic? Vision language model says yes. And then the large language model can then determine, okay, go to the right cup, which is this one, pick up the cup, bring to human done. And that will tell it how much it should squeeze, how wide it should have its hand, things like that. This one, Prog Prompt, the author I recognize here is Jesse Thomason, who's at, I believe, USC, does really, really interesting research, also interested in grounding. They have a GPT-3 model, and they have basically two instances of it. What they want their model to do is this. There's a lot here, but I'll walk you through it. Here's a language model, and here's a language model. And it's kind of this stuff on the left is for this language model. What they do is to get a robot to do things, to move and to act, is they will give it a prompt. So from actions import walk, and you'll notice that each of these actions have objects associated with them or not. And then these are the objects that are in the room, and these objects might come from, for example, the robot scans the room with its camera, and an object detector just kind of populates this. And then what they want it to be able to do is give it the name of a function. This looks like Python code, throw away line, and it's supposed to fill in then all of this. That's what the language model is supposed to do. So given all of this stuff up here, the imports, the objects, and the examples, as a prompt, it's supposed to then create the next set of actions for this prompt. So microwave salmon. So if we look at microwave salmon, what the model would output is walk to the kitchen, find the microwave, and then you can make some assertions that if the microwave's closed, then go ahead and open it. Make sure the salmon's in the hands. If it's not, go find the salmon, pick it up, put it in the microwave, and then there's all this stuff of turning on the microwave and so on. So the input is something that looks like Python code. The output is something that looks like Python code, but it's really nice because this gives a set of actions that the robot can take that can easily just be called on the robot. This language model is meant for maintaining the state. So information about where, like, is the microwave open? Is the salmon in the hand? That's all information that's fed through here. So the fridge is closed, the light switch is on, and so on. And you can make assertions. And this is information that tells the robot where it is and what actions it can take right now. Because if it's standing in one place, right in front of the microwave, it can do stuff with the microwave, but if it's not right in front of the microwave, it needs to go to the microwave. And this is where that knowledge of where the robot is encoded. Finally, the last paper I'll review in this part of my talk is called One Piece. And if you haven't heard of this, I think this is a really important paper. So this has a different take on how to get information into a language model and how to fuse the information from different places. So here's 3 modalities: vision, audio, and language. They call these things adapters. And adapters don't take tokens, they take vectors, or they take embeddings. So you have some way of representing the visual world in the adapter. You have some way of representing the audio in the adapter, whether it's a transcription of what is uttered or whether it's noise that happened in conjunction with what was happening in the image. And the 2 boys playing frisbee on the grass would come to it as an embedding from the embedding layer. And that the way it's fused is with self-attention. Self-attention, in this case, really is all you need for their model. And self-attention is the thing that's doing the grounding, as it were. So it's making bits of language, the encoding of language mapped to different bits of the vision adapter, and so on. And then that splits off the feed-forward neural network that we always see in the attention heads. And they have their own kind of say in what's happening. Won't go into any more detail than that, but this is an interesting difference from the other ones we've seen. So there's 2 takeaways from looking at these papers. How can we get information into and out of language models that might be useful for robots? The first is we can convert the physical world into tokens, and then we can fine-tune a pre-trained large language model on input-output at the level of symbolic tokens, and we saw things like tuples or even Python code. The other way is to represent the physical world at a more fine-grained level, usually in the form of a vector, and fuse that or those vectors within the model, for example, using self-attention like we just saw with the one-piece model. Which one is better? It really depends on what you want. Most roboticists don't want to deal with language, so if they can represent the world in symbolic tokens and pass that to language models and only have to fine-tune a language model, great. And that if that works for the types of research questions that they have, then wonderful. But if you are a researcher that's more interested in the robot itself learning in an interactive setting, and maybe like if you're interested in grounding, for example, this might be a little bit more representing the physical world at a more fine-grained level might be what you are interested in, depending on your research questions. So that was the second part of my talk. I'm now moving to the third part of my talk. I want to talk about what I'm calling a robot-ready spoken dialogue system. I haven't talked about spoken dialogue just yet. Challenges using large language models for spoken dialogue systems with robots, and then some ongoing work in my lab at Boise State University called the Speech, Language, and Interactive Machines, or SLIM Lab. First, there's a lot of meetings that have happened, workshops and so on, where researchers who are interested in speech or dialogue or language interaction with robots have gotten together and talked about kind of the research trends, what's happening now, and made recommendations for future research. There's me, but there's like 30 authors on this paper, and it's really good. It's actually you can read it. We paid to have it open access. Part of the one outcome of these discussions was we really wanted something. Of course, everyone wants something you can just take off the shelf and use. But what we really wanted was a basic dialogue system that had the requirements that would allow any robotics researcher who wants to have spoken dialogue or be able to speak to their robot to have a piece of software that you could pull off the shelf and use that wasn't too difficult to set up. So we published this paper in 2020 at the SIGDIAL conference called RRSDS, or Towards a Robot Ready Spoken Dialogue System. It was a demo. And the requirements we came up with were that the dialogue system has to be modular, multimodal, incremental, distributed, and temporally aligned. And I will now tell you what I mean by all of those things. Modularity, we've seen large language models are trained end-to-end, but they can be used as modules within a robot system. We've seen examples of that. Number 2, recent large language models are becoming more multimodal. For example, One Piece, or that list of 30 papers that I showed you that use vision language transformers. Those are multimodal language models, which is nice. Now they're kind of reaching out and grabbing the physical world and incorporating that in the model. Number 3, incrementality. What I mean by incrementality is this. As I am speaking, you are listening to what I am saying, and every word I say, you are updating your understanding state. That's what I mean by incrementality. It means you're not waiting for me to stop talking before you process. I am talking over time, you are listening over time, and you are understanding over time. In terms of a system, like a dialogue system, incrementality usually means it operates at the word level. So instead of taking a speech recognizer and talking and it outputs a long utterance, a sentence, a transcription, and that long sentence transcription goes into a language understanding model, like a large language model. We want it to operate at the word level. So the speech recognizer outputs a word, the language model takes that word in, and then the speech recognizer outputs the next word, and the language model takes in the next word, and it maintains its state.
Slow down. Just a little bit, slow down.
Okay, I will. So language models are not inherently incremental, at least on the input. They output one word at a time. That's the nature of the autoregression. But they aren't incremental for understanding. Usually when you use a language model, you give it a big prompt, and then you give it fully formed sentences. But that's not how humans talk to each other. So if we want to talk to robots, we have to move more towards incremental processing. There is work from David Schlangen's lab. He was my PhD advisor. He's now in the University of Potsdam, and some of his students, Berlin, for example, is doing some really interesting work on making language models not fully incremental, but at least making them useful in an incremental way. Modular systems can be easily distributed, and this is just a technical requirement. If I have 2 language models that are local, and I have a speech recognizer that are all local, they all have to have their own hardware, and often that means they're all running on a separate machine, a separate computer, and I have to make sure they can talk to each other. That's what I mean by distributed. And large language models input is not temporal in nature. Temporal meaning, I recognize that sequences are tokenized and that they even have token indices, but here's what I mean by time alignment. You might be familiar with Charles Schmott's work from 1979. Put that there, so if someone might point, so this is back. You can use a didactic gesture to point at an object, say this one here, and say, put that, as you point at it, there, and you find a dark spot, and you say, put that there. So the word that is accompanied by a didactic gesture, a pointing gesture. The word there is accompanied by a separate pointing gesture, and those occur in time. They're time aligned. Those are 2 modalities of information that we have to align temporally. That accompanied by a gesture, there accompanied by a gesture. And we can't really do that with language models. Temporal alignment isn't as important. It's sort of a ping pong game at the moment. So incrementality and time alignment are very tied to each other here. I do want to talk briefly about infrastructure. So one thing about language models is they're trained on text, and that's partly because text is easy to find. So the kind of research that we want to do when it comes to robots is it's harder to collect the data because we have to have very expensive hardware. Well, everyone wants more GPUs, even if you're just using language models. But we have the robots themselves. We have maybe computers that are running different modules that the robots connect to and use. In my lab, we have multiple GPUs just to run one small robot because there's so many complex modules in the system. You have to have software that puts it all together. We use something called Redico. It's a Python package that has a lot of modules associated with it. It is incremental. There's speech recognizers, language understanding components, things like that with it that I really like. We use it all the time. The platform for situated intelligence, or SCI, is written in C#. It's put out by Microsoft Research, Dan Bohus's group. But we have them work together. So Redico operates a lot of modules, but it does. We use some SCI modules as well. Together, they fulfill the 5 robot-ready spoken dialogue system requirements. We have logging tools that comes with SCI as well. We have to have distributed coupling between the robots and our software. And the robot has to have a certain number of capabilities. These are my capabilities that I'm interested in. Not everyone who is using robots is interested in these capabilities, but I want it to have camera, wheel, speech synthesis, and a face. I wanted to have object detection, segmentation, not recognition. I don't care what it thinks the objects are. It's often wrong. So we have used YOLO. We're working with SAM right now. The segment anything module. This doesn't label objects. It just tells me where bounding boxes or regions are. Clipper Dino to represent them as a vector. Dino is probably a little bit more plausible for the kinds of things I'm interested in. We also need something called object permanence, and I'll talk about this on the next slide. We need something, for example, to generate novel emotional displays and the recognition of emotional state of self, which I'll get to in a couple of slides. We also need navigation and exploration, as well as building up bottom-up categories. And these are all current work. So these are the robots we use. We have 2 Misty robots, and we have a handful of Cosmo robots. The Cosmo robots are very important because they're small. They have a cute voice, so people treat them like they would treat a child. Whereas if someone walks up to Misty and they've never interacted with Misty before, they have this expectation that Misty can see them and that they can talk to it like an adult, even if we tell them that's not happening. But with Cosmo, they look at it and they're like, oh, it's so cute, and they treat it like it's a 2 or 3-year-old. So the first thing we need is that objects can learn object references and remember locations. So the big player here is what's called the simultaneously locations and mapping module, or SLAM. This is a heavily developed research area in robotics, because robots need to know where they are. They need to move around, and they need to not bump into things. So they have to remember where objects are. So they have to map their environment. And that kind of looks like this in a virtual space. So if Cosmo's driving around on a table and it moves and it looks to the left, YOLO tells it, oh, there's an object there. It draws a bounding box around an object, and we can get its rough size. Then SLAM instantiates an object there, though we don't know what the object is. It's just there. And then if it turns over here and sees another one, it puts it there. And that's important because for this particular research that we did, a lot of times robots are moving around and they see objects, and someone might use a word like, oh, that's blue, or that's a vase. And the robot might do some degree of grounding, whatever the model is for that. But then if they ask, where was it? Right? Where's the blue vase? It won't remember where it was. So location of objects is something that humans can do, and it plays into understanding what objects are. So this is a complex system. You can see it's distributed. It's modular. We have a speech recognizer that goes into what we call a grounded semantics module, which is no more than I'm going to take a featurized vector of an object. So a bounding box from this, pull out the bounding box in that sub-image, pass it through clip. Now we have a feature vector for that object that is input into our model, and we train a classifier for each individual word. So blue gets its own positive and negative training samples, vase gets its own positive and negative training samples, and whatever words it hears. And then it navigates, it speaks. And what's important here is someone can teach the robot. They can say, oh, that's blue, or that's a vase, or that's a cup, or that's a mug. We have a bunch of objects on the table. But then they can quiz the robot. They can say, Cosmo, where's the vase? And it has to drive back to the vase directly. It can't just mope around and try to find an object that randomly make turns and things and find the vase. It has to drive directly to it. And that's what SLAM helps us with. Now I'm going to talk about emotion. What I mean by emotion is a signal of an internal state of being. There's a lot more to emotion. There's a lot more to affect, feelings, mood, those kinds of things. But I'm using these on robots, at least I'm claiming to. And the only thing I can really claim is that the robot can signal an internal state of being by its actions. So emotion, and there's a reason why I think this is important. And it's because emotion is both pre-linguistic and cultural. Pre-linguistic meaning, children are born, they're very young, they can't speak yet. But they have, they can cry, they can get angry, they have emotions. The degree of emotionality, it's more at the affective level. So it's valence, positive, negative valence, it's arousal, those kinds of things. And as we get older, emotions, at least according to Lisa Feldman Barrett, and others, culture and emotion are tied to each other. So the way someone in the United States might display anger is different than the way someone displays anger in a place like Japan. And that's tied to the linguistic system. They kind of grow together. So there's two things I want. Well, we'll dig in here a little bit more. Furthermore, humans anthropomorphize robots as having emotion, no matter what action that robot performs. And this is work by Yekaterina Novikova. We've seen this in our lab in some of our research. The robot moves, people will assign emotion to it. They appraise it for emotional content constantly, even if we tell them not to, even if we beg them and tell them that the robot doesn't feel, it has no feelings, please stop saying it's happy or sad, they will still do it. So we can't avoid it. The third is this, and this is something I actually came out of a discussion when Friedrich Bullermüller gave a talk in the 2020 Cognitive Informatics Seminar. I asked him if you were to represent emotion technically on a robot, how would you do it? And he said, I would use the motor system. So that's kind of the back door we're using here. We use appraisal theory, which has been around for a while, but has been well studied on virtual agents. And the idea here is we can represent robotic emotions via their actions by having humans appraise the robot actions. So it's not the human emotions, right? We're not looking at human faces or anything like that. We have a human come in the lab. We have the robots do things. And the humans will write down descriptions of what they see, and they will appraise the robots for having emotion as the robot is acting. So, and we've published quite a bit on this in several conferences. So here's what we're trying to do is get two models out of this. And this is funded by the National Science Foundation. The first model is what we call an emotion recognition model. So the robot acts, right, behaves, and we can take the motor system, right? That's what we want. That's the internal states. Those change over time. It's a vector that represents if the lift is up, if it's moving left, where its head is facing, those kinds of things. And then whatever's happening on the face, of course, will display emotional qualities, and then audio. So, and this is a time series. And so we featureize those and we train a model with our data. And the output of this model is a distribution over 16 emotions split into 8 valence pairs. So interest, alarm, confuse, understand, frustration, relief, sorrow, joy, anger, gratitude, fear, hope, boredom, surprise, disgust, desire. And we didn't make these up. We got these from Johnson. This was back in, I forget which year this was. Psychological literature, this is always a discussion point. Should we use fewer emotions, more emotions, have it be more fine-grained? This seemed like a good start, and we can add more later if we want to, but this is what we can deal with at the moment. And we like these emotions because we want the robot to have to be able to display these kinds of emotions, things like confusion and understanding. That's really important for the robot to display when it can't speak yet, or disgust, or boredom, or surprise, or interest is a very common one that people think the robot has. So we want this to kind of give to our system to know, like, what's the quote unquote internal state, emotional state of the robot. And the other thing that this is going to be important for is if we have a model of emotion like this over time and the robot is learning language, we can get a distribution over these emotions, right? This outputs a probability distribution over these emotions. And that forms a vector that we can then use to enrich a language model. That's our future goal here. So this model serves two purposes. The other model we want is a generative model. So in this case, we want to be able to give it an emotion like from our set here, something like confusion, just a symbol, and the model outputs the individual actions that we would have the robot take. So we call these functions basically: display this face, move your head here, move your lift here, drive your track there, move your head here, over time. And if someone watching the robot as it performs these actions into a behavior like this, someone watching that would appraise it as confusion. That's what we want this model to do, is label to sequence. And we've seen that can be done. with large language models. So this will likely be a large language model. We've been working on it with some degree of success, though we have some work to do. Taken together, what's really important here is we want the robot to display emotions, because that helps humans buy into the robot and interact with it more. They want to help it more, we've noticed, than if they don't. They interact with it more, they talk with it more, they're more bought into helping it learn words. So this is important, but then we also want the emotional state to know, like, what should it do next? And we also want to use this to enrich language models. So it helps with the interactive qualities, but it also helps with the modeling. The next thing we really need is that we need smaller language models for our particular research, because we need them to learn without huge amounts of data. So at the moment, language models need a lot of data to train and work properly. Our question is, can we still use a transformer language model if there's very little training data? For example, 5 million training tokens. 5 million is roughly what we've seen estimates of how many words a child learns before they begin to say their first actual, lexeme words. And we have 2 papers that were accepted to CONL this year. One of them was part of the Baby LM challenge, which I'll talk about in a moment. And then the next question is, can small language models work on multimodal data? And this is current work that Clayton Fields, my PhD student, is working on. So these 2 are just a hint, because these haven't been published yet. They've been accepted to CONL, the Conference on Natural Language Learning, which is an ACL conference in Singapore this year with EMNLP. So one of them is making a small transformer, and we tried a lot of different things. We looked at different architectures. We found that the Electra model was a really good place to start, and we were able to get a smaller embedding layer, smaller everything really, a smaller hidden layer for sure, but we made it deeper, and it worked as well as models that had 10 times as many parameters on, for example, the glue tasks. The other thing we did, this was part of the Baby LM challenge, which its inaugural year was this year. Very quickly, we had vectors representing visual vectors and vectors from the Lancaster sensory motor norms that we would call sensory motor vectors. And we converted vectors into a multiplex network. And so we had things like sun and ball from the visual vectors. If they had a close cosine distance, we put a link between them. And these 2 have similar shapes, so they have a link. But ball and kick are similar to each other in sensory motor world. So if someone hears the word ball or hears the word kick, they're kind of associated with each other. So we get this complex multiplex network with thousands of nodes and tens of thousands of links between the nodes. And then we throw away these vectors, and we translate from these vectors from this network to these vectors. So we have a vector again for each word, but it's a fusion of information from these 2 modalities. And then we enrich a language model with that by just swapping the embedding layer, which is similar to work I did in 2020. We just tie the embedding weights, and it worked a lot. It was interesting because with much less training data, the model was able to learn and do as well as models, again, 10 times its size or even bigger. Okay. The last part of my talk here is I'm going to talk about grounding finally and define it for you, and it's kind of convoluted, so hang in there with me. What I mean by grounding is a robot explores its environment, it sees objects aren't labeled, but the robot can categorize them into different categories based on visual and spatial features. Someone can then come along and label them, for example, cat. The grounding happens when the label is uttered. Use the collected prior knowledge of the object and train a classifier using positive and negative samples of the category, called contrast, similar to contrastive learning. So grounding is bottom up. And the goal is to endow the robot with exploratory behavior, right? We have emotion behaviors, but we want the robot to explore an environment, and we don't just want to have it randomly explore an environment. We want it to look like it's exploring on purpose, as it were. And this is building on Pierre Oudier's lab that results in the robot building categories as it explores. So here's what we're doing. This is work by Catherine Henry, a master's student here. We're starting very simply to make sure we're being as true as possible to Oudier's lab and the prior work. So there's 2 objects in a scene, and here's the robot. And the robot can see in front of it. And if it turns to the left here a little bit, we would get a bounding box, and then we'd extract that and represent that as a vector, like through clip. And that gets passed through the model. And the model is what we get from PRVDA's lab, the curiosity model. And what we want the curiosity model to do is develop categories from the bottom up. So the robot, when it begins, doesn't know anything, and it has 3 actions it can take, basically. It can, well, 4 actions. It can rotate left or right, and it can determine what number of degrees it can rotate, and it can move forward or backwards. So it's exploring its space, but it's a very simple exploration of rotation and a little bit of forward and backward movement. But to help it decide, the model is the thing that decides how much, which way it should go, which action it should take, and how much. So the model decides, okay, I'm going to turn left, and I'm going to turn left 40 degrees. And what is important here is that if it turns left 40 degrees, what's going to happen? The model predicts that it will see something that it has seen before. And if it sees something that it has seen before, that means the model has learned something about that category and that it was able to predict that it was there. Whereas if it moves somewhere and something unexpected happens, something it didn't predict, then that's where learning actually occurs. So let me walk you through this thing on the right here. When this starts out, it's a big gray box. Each of these dots represents an observation that the robot made. There's hundreds of them in here. So the robot runs for, I think, at least an hour. It moves, makes an observation. That observation is brought into the model and determined, is it surprised, is it not? And that's placed somewhere here. And the x-axis is degree of rotation, y-axis is how forward or backward it's moving. So how far back, close it is to the, up here it would be closer to the objects, back down here it's farther away from the objects. And the color is kind of in the 3rd dimension, represents region learning potential. And as it learns, it's kind of in this tree structure that we've represented here as just rectangles, as grids. And if the robot starts here and has a degree of rotation in these thresholds, it has all these observations, and this happens to be where it would see this object right here. We would recognize that as an elephant. But the robot, you'll see there's kind of this hard line of, if I'm at this degree of rotation, I can see something. If I'm at this degree of rotation, I see white space, and that's not interesting, or that's too predictable. So it looks at this a lot. And what we want is each of these subcategories come to play. So we can see that right here, if it's far enough back, it looks at the elephant and it categorizes it separately from anything else in the space. And then there's subcategories of it. For example, this stuff on the left, we can see is probably what it's categorizing as the elephant's trunk. And these categories are built bottom up. It has no idea what these categories are other than that they belong together somehow. The cat wasn't so much. We had to be a little bit closer to the cat to get different categories out of it, or even get it into one category. And high potential means that there's unexpected things happening. So this is kind of halfway through the interaction. It probably just hasn't observed the cat very much. Over time, these kind of settle on the colors down here. But this is changing dynamically over time. So it starts very red and moves its way down. Okay, so that's some of the research that we're doing. And like I said, what we really want is a robot that has some really key capabilities as it's beginning to start grounding and learning language. It needs some degree of emotionality, at least in its display and how it acts, but also in its internal state knowledge. The robot needs to be able to remember where objects were, and it needs to also build up bottom-up categories as it's exploring its space. And the way it explores its space can't just be random movements. It has to be more intentional, which is why we're building up using this prior work. So all of these things work together for a robot that what we want is we can put it in on a table, at least Cosmo, with a bunch of objects, and it's intelligent lookingly drives around the space. It looks at objects, and people can tell the robot that's what this object is, or query or quiz the robot, and it's building up from the ground up. One thing I didn't mention, once it gets a category like this, it's saved all of these vectors that represent the objects, and we can then ground those into the language side and use, for example, a classifier. So that's what we want to do. We are using language models to some degree, and we do want to use this knowledge to enrich language models. That's what my career award is from the National Science Foundation. But what's really important is that we're trying to do this in, I guess, a little bit more developmentally plausible way. David Schlangen has pointed out that what's happening with language models is they're going in the opposite direction. They're starting with text, and then they're working their way to vision, and then other modalities, and then embodiment, and then who knows where they'll end up getting. Whereas child, or human development goes in the opposite direction. And they may get there, but I have a feeling that the way that large language models are being trained and used, the learning progression is going to get us so far, no matter how big the models are, no matter how much training data we give them. So to conclude, large language models are increasingly multimodal. That's great. Large language models are increasingly being used in robots. That's also great. They're being used for planning, for interaction, their pre-trained nature allows out-of-the-box usage, which roboticists really like. Large language models don't solve all of the problems we have in robots. For example, they can be used for understanding speech in some circumstances, but not others. They can't be used incrementally, not time-aligned, at least not at the moment. The notion of grounding is somewhat vague in the literature, and learning while interacting seems doable, but technical and modeling challenges remain. So here's some references, and I want to thank you for your attention and for being here today.
Okay, that's terrific. We'll start with the questions. Can you see? It usually takes a little while, as you recall, for questions to.
Of course.
So I'm never at a loss. Can I ask you about the natural question? Is you say bottom up, and I understand what you mean by bottom up, but we have these large language models, which are already by their nature top down. They're words.
Yeah.
What's the relation between words gained bottom up and words stolen from a big gulp?
Yeah, and that's what I meant when I said there's two ways that we can use language models on robots. One is at the token level, and one is at the finer grained kind of vector level. And most people are perfectly happy with dealing at the token level, and they don't care that it's top-down learned, and they may even claim that they're doing grounding. But if the nature of your research is that you want to address grounding, or at least approach it in some way, then I think you can't do that. It has to be bottom up. So if that's why another reason why I want a small language model is, okay, if I have a language model that's heard, I guess, text, 5 million tokens, we don't really know what those mean, then we can bring that in and use it. But there still has to be bottom up learning of categories in terms of how they map to the visual world. For example, a mug or a vase or a ball or a chair. That language models aren't doing that, and the visual language models aren't doing that either, from what I can tell, because often they're pre-trained on a bunch of text, they're pre-trained on vision stuff, and then there's something that brings them together. And some of the representations are at the symbolic level. I'm trying to get at your question here, but I have to build it in a little bit. So like when I say bottom up, what I'm saying is, like I'm using CLIP, and that's cheating because that's a language model that has vision. That's why we're moving to Dino. Dino is a little bit more plausible in how it's been trained. The vectors it's not tied with language at that point. It's only vision. And the vectors are better than what we get from something like VGG19 or some other Keras model from a CNN. So that I like that a lot better. It's not tied to language just yet. And then that's what we're doing. So we're using that to represent the objects. The bottom-up categories are built from that. Language has nothing to do with it at that point. And then once people start talking to the robot, it can tie what it hears to the words or the categories that it has built up.
That's great. We've already got a question, Gary. Yeah,
Hi, Gary.
Yeah, hi. I guess I have two questions. One's a real question, and then the other is kind of a point of information.
Okay.
So when you talked about the robot that had to clean the pan, right? It had a step in it where it said, if you don't have the pan in your hand, get the pan or something like that.
Right, right.
Which reminded me a lot of the frame problem that we used to talk about in planning. I haven't followed planning for quite a while, but you know, the frame problem is you had to basically prove that your plan was going to work, and you had to be able to deal with all the possible exceptions that might happen.
Right.
And that's why we moved to more probabilistic models where you pick the most likely plan to work and not worry about all the exceptions until you get there.
Right.
Is there a frame problem here or not?
There will be. There's a frame problem still. I mean, people are using large language models to, right? You can put the state in them and they can maintain the state, but it's gonna make mistakes, obviously. And then the plan that it comes up with isn't going to be the perfect plan. The assertions help, like with the prog prompt one, there's assertions of, okay, if I'm not in this state, then this is what you do to get to this state. So in that case, it's kind of making a high level plan, but the frame of, okay, I might not be in the state I want to be to do the next thing, let's do a quick check. So that's just on the fly checking. But yeah, the planning literature is still really burgeoning in this area, but people are moving to large language models for getting these plans, just like they are, because what they want ultimately is that the plans are generated automatically and autonomously without having as much pre-training, and they're getting some traction out of language models for that. I wouldn't say it's been solved though.
Could you just give a quick definition of the frame problem for those who might not be initiated?
Gary, why don't you help us out?
Okay, I thought I sort of said what it was. So the official version, I think, is you know, if I change state, you know, does the paint on the wall change as I change state, or does it stay the same? That is, what changes as I go through steps in actions, and what remains the same?
And what does that matter to the actions that I need to take?
Yeah.
Right.
I think I've said everything I remember from about the.
Okay, it's not an exam. It's okay. Steve.
Anyway, yeah, so I had another question, which was more of an information question. So when you showed the little robot learning from the ground up, looking at the elephant and the cat,
yeah,
I didn't really know what this diagram you showed meant. And I don't know if anyone else did either. So you had
okay.
you had dots in a square or a rectangle, and I didn't know really what this meant at all.
Well, I'm not doing it justice. Catherine could probably do a better job, but we actually went over it yesterday. The hard part, what's really hard, there's a lot of stuff going on in this interplay, right? The robot is moving left and right, it's moving forward and back. It's kind of has this fixed starting point. That's what this is. So this is kind of where the robot starts, and then it makes a decision: how much do I move left, or how much do I do? How much can I move right? So after it exits the fixed starting point in its first action, it can kind of do whatever it wants. But once in a while, we have to check to make sure it's lined up okay. That's all that is. But this movement left and right, it sees these objects, and each instance of seeing an object, that's a dot here. So and these dots have to do with the degree of rotation from the fixed point that we're working with. So just a little bit to the left of the fixed point is where you'd see the robot, and a lot more to the left of the fixed point is where you'd see the cat. So that's kind of where at least this axis is coming from, and each of these are points. If we just kind of flatten this on the on the x-axis, it'd have a bunch of points that are just on elephant, fewer on cat, but way fewer on just white space, because all this stuff out here is just white space, and the stuff between them is just white space. The y-axis, which we can't really see, is how close it is to the object. So this is as far, I think it can go a little bit farther back, but if it backs up and looks at the elephant, that would be back here. But if it drove closer to the elephant and it was really close to it, that would be like this one right here, and then everything in between. Okay, so the grids here, so what's happening, let's see. So there's the model is, you can think of it as a tree that is kind of branching from what it expects to see versus what it actually sees. And if it's something new that it didn't expect, then it can take a branch. And the branches are important here because that is how we get object categories to separate from each other. And kind of what we end, sorry, go ahead.
So one confusion here is the cat's at minus 140 something degrees, and yet on the x-axis here it goes to minus 140 and there's not much there.
Sorry, it's positive 40. These are tildes. So it's about 40 degrees to the middle of the elephant, and it's about 145 degrees to the middle of the cat. So yeah, yeah, good for calling that out.
And then the y-axis is like your distance from it, or
yeah,
what?
The distance from it. So if the robot's really close to the elephant, if it drives right up in front of it, that would be I think that's this up here. And if it's farther away from it, then that's down here. I actually might have that backwards. And then the colors are this thing, the region learning potential. So it's kind of, if it's darker like this, kind of this darker purple gray color, it's settled on, it thinks it has a category, and going back over here isn't going to help it learn any new categories. But there's stuff over here that it hasn't explored yet that it needs to explore. That's kind of the curiosity part of it. Like, I'm going in a future exploration, I'm going to go and try to find myself in these states so I can explore them a bit more. And that's what the model helps with.
Yeah, we used to have a measure of interest that was the error in the output.
Right.
In my old model of learning the past tense. It sounds like that's become a common curiosity thing.
Yeah, I admit I haven't looked into that as much as I should have, but I will. We are finding more and more work that has done things in this area, but the big ones are, well, Pierre Oudier's one that we've been really looking at.
Yeah.
He was here earlier, but he had to leave, unfortunately.
Oh.
He'll be talking later in the series. Okay, so let's move to Steve Hansen and then to Munir Bukadoum. Go ahead, Steve.
Yeah, can you hear me?
Yes.
Great. Great talk. And I love your approach, Casey, to creating this sort of systematic analysis of the chatbot or the transformer technologies and then robotic technologies, and then melding them together in a careful, thoughtful way, but also looking at, different kinds of deep learning kinds of approaches to categorization and to integrate that and so on and so forth. Now, if that's fair, now, one of the things that a lot of us suspect is there's a scaling kind of phenomena going on here with regard to going from, probably, I forget what ChatGPT 2 was, maybe, 60 billion weights, and now we're up to almost 800 billion or something. And there's clearly something odd about learning everything from, let's say, inside of a library. You're just reading everything, which is what's happening. And you don't have any possibility of grounding. And you just read something, about cooking or about fly fishing or whatever, you can't do it. And so there's this disconnect, and we could, roughly call that kind of a grounding problem. So there's a recent, very cute demo that Boston Dynamics did where they took a ChatGPT and they dropped it inside of their robot dog called Spot. Have you seen this demo? And a lot of things emerged from this, which was sort of shocking in the way that it actually constructed the reality of moving through space and making inferences and judgments. But there's simple psychophysical things we don't understand here. So for instance, if we just did that experiment, put a ChatGPT, a 900 billion weight ChatGPT inside a robot, and then sort of watch what happens. Even simple things like, are you in a Euclidean space? Do you know you're in an upright gravitational field? Do you understand that this is actually Euclidean and not Riemannian space? You're not on a sphere. These seem to be like precursor questions you'd like to get at prior to your sort of more, I think in some ways challenging, but also more aggressive movement in this direction, which again, I can't say enough about. I think it's important and you know, should be at NIPS, for example, and some of the robot games that they're planning. But anyway, that's some thoughts. I'm curious what you think.
Yeah, I mean, for example, the first paper that I showed, the tool former, basically language models can teach themselves to use, but they have to have 775 million parameters minimally. If it's any less than that, then all bets are off. After that, it can do well. It's a lot of parameters. I mean, it's not as big as the models we have now, but it's still quite a bit. So as for putting just a large language model on a robot, they have to hook it up somehow. I mean, if you put a large language model on a robot and people can then maybe talk to it, the robot doesn't do anything, but they can talk to it. That's fine. But if they're using the language model to do things like reason about its environment, or like, let's say it has a visual component that it can see there's a bridge up ahead. So it knows what it knows about bridges, but then it can query the language model. What do you know about bridges? And they can explain things like, well, bridge is this, bridge is that, and maybe bridges need to be big enough for you to cross over, or they need to have a certain weight tolerance. So you might be too heavy. How heavy are you? And then you can reason, well, how heavy am I? And if you know that, great. And if you know the tolerance for that particular bridge, also great. But we kind of know just by looking at it, yeah, that bridge will hold me up. And that's probably not something that the robots can do yet, even if you can reason with a language model. But you know, the fact that you can kind of get at that is nice. But I'm kind of in agreement that text is kind of this top-down, pure symbolic thing. It does really well with syntax, and it seems to do some degree of composition. So I don't just want to say, they aren't doing grounding properly, let's throw them away. Clearly, they're doing something. And there's some things they're doing really well that we shouldn't ignore, like syntax. So that's why I think this push to the vision transformers is really interesting, because that's showing us how kind of these concrete concepts can be connected to these abstract ones that are just right. So if I'm going to learn about the word ball, I need to experience the ball, touch it, look at it, and see it, that kind of thing. But the word democracy is this abstract thing, and I can just learn about that from text. That's fine. So kind of moving from abstract back down to concrete is what these visual transformers are doing, and that's kind of the direction the entire field's going in. But I think that's always been the hard part. The sensory input has always been the hard part of trying to reconcile perception with cognition. That's not easy. And I don't think language models are going to solve all the problems there.
Yeah, no, I agree. In this demo, though, the Boston Dynamics people did have a visual input. They also had infrared,
right?
And they could also speak to it. And the main task of the robot was to go through the Boston Dynamics Museum and basically tour people through it. To meet people at the front door, walk them through it, and find out things. At some point, they asked the robot, who were your parents? And it walked through the museum, found version 1 of the Spot robot and said, pointed at it. Now,
yeah.
So none of this is staged, and so it's both a little creepy, but it's also somewhat interesting about how grounding might develop in such a system that has symbolic structure like text and has no relationship to the world. And this is why I worry about the psychophysics of this. What could a thing like this know about the
parentage
physics that it's dealing with?
Right. No, I agree. They're also capitalizing on the anthropomorphization that people see this robot, they can talk to it, and whatever actions it takes, if it appears to have a behavior that is smart or intelligent looking, they're going to attribute that to it knowing language and it knowing all that stuff. But what's actually happening in the model might be very different from the kinds of processes that humans go through when they're thinking.
Yeah. Well, no doubt.
Okay, let's now move to Munir. Turn on your mic. That's it.
All right. Well, great talk indeed, and thanks for sharing your knowledge with us.
Thank you.
My question is a very practical one, actually. It's what kind of processing gear do we need to embed in those robotic brains to implement all these algorithms? And
Yeah.
can you do real-time operation with those?
Our goal is real-time operation. That's the incrementality, that's the time alignment. Our goal is real-time operation. That's another reason why we want small language models. That's one reason why we put speech recognizers on machines in our lab instead of using like cloud speech recognition, because the latency is too long. It has to be fast. That's one very important requirement. So the hardware that we have isn't on the robot itself. We're kind of remote controlling the robot with our networked distributed GPUs and everything like that. The robot's kind of an avatar out there, but it is in the real world. So some robot assists are very strict about anything they do has to be on the robot itself. The hardware, the battery, everything has to be on the robot. So if you're going to do speech recognition, it had better be on the robot. Some people are a little bit more lax. They're happy to use cloud computing resources. For us, it's kind of in the middle. We want to use what's on the robot if it's available. Like the Misty robot has some pretty powerful hardware. It can run some things really well, but Cosmo has nothing. Cosmo is pretty weak. It has enough to connect to it with Wi-Fi and perform the actions we want it to. And then, of course, take in the perceptive stuff like the camera. But that's it. We couldn't run anything on Cosmo.
Okay. So basically right now you're kind of remotely controlling all this.
That's right.
Yeah.
Okay, next question, Jean-Guy Bernier. Turn on your microphone.
Sorry about that. Thank you very much for this very stimulating intellectual presentation. I work in the department with computer scientists, but I'm more in philosophy, and your presentation rose many philosophical questions, and
For sure.
the first one is the grounding. It's a very classical philosophical problem that knowledge must be grounded. It's very traditional to, at least in some part of philosophy. Stephen convinced us that you must ground. But once you've picked up the information from your grounding, what I find fascinating in the presentation is how do you manipulate what you found in the groundings? You call them, you said the grounding categorizes, but you have many types of categories. Now you start working on the categories themselves. You can't say there that when I manipulate these categories, I need to ground myself on these categories. It'd be in a vicious circle. The categories themselves have to be manipulated in a certain way. Be sensitive to the time, to the space, to the causality. Are there any philosophers you've seen that are translating this problem of second level categories and you implement them in a computational way, the thesis that you must be able to categorize categories in a certain ways. And one illustration that came, one of your presentation or last slide about the elephant and the cat, is you said, well, I see in the results some subcategories. These subcategories are not grounded on the perceptions. They seem to be grounding on, could they be grounded on the fact that the cat or the elephant is grounding something, or is building categories about the position, about the time, or about the causality, or something else? We're at a second level structure. And there there's a hypothesis on the fact that when you're working with robots, you need a second level type of categories and there you're meeting philosophies or philosophers very frontally.
Well, it's great discussion, great question, and I'd like to think that I understood your question completely, but I'm not actually sure that I did, because you're getting into the philosophical trenches here. What I think you mean here, I'm going to go ahead and try to at least say something in response to that. What I've become interested in is the fact that we have concrete concepts and abstract concepts. I frame a lot of what I do in that kind of space with concrete concepts, and we have a lot of them, and they're largely the concepts that children learn early in life. Those are by and large grounded somehow. Sometimes it's visual, sometimes it's sensory motor, sometimes it's every sense input, sometimes it's time, location, but also feeling, right? Emotion. Those are all part of it. As time goes by, I think when a child is about 12 years old, they're still at about 60% concrete concepts, but they're getting more abstract concepts as they go along. And then, of course, when you get to university level, most of the stuff you learn about is abstract, except for, if you're in nursing, you're learning about body parts. It's very concrete. If you're in electronics, you're learning about circuitry. Some of that's very concrete, but when we talk about it, we talk about it very abstractly. The language models, when they're trained on text, are purely abstract, as we can kind of recognize. That's actually something that's difficult to convince people of. They're assuming abstractness of all concepts, as it were, all categories. So no concreteness to them. So, but you are right. Let's say we have a model that, let's say that my dreams come true, and I have a model that can build bottom-up categories, and it can scale well. It can get all the modalities I want. It can interact really nicely with humans, and I get a lot of vocabulary out of it that's grounded, and I can bring that into a language model, and I have emotion. Say all of my dreams come true. I think you're still saying that's still not quite going to get at the philosophical questions here that we're asking, which is things like, well, what actually is it grounding into? We give it vectors, and the vectors can come from different places, like from vision. We represent an object as a vector. You can represent and you can add to that things like the degree of rotation. That's part of it. Or you can add how close I am to an object, how far I am to an object. You can also add affordance information to it, like what kind of actions can I take on this object? That's something we're not doing. That's something that Udier's lab did, other than we can look at an object. So we're not solving all of the problems, all of the philosophical conundrums that come from this line of research. But I think we are moving the needle ahead. I do want to explore this, though, this thought you're having of, because I'm not quite sure I'm answering it or getting at it the way you would like.
Unfortunately, we were running out of time. So Jean-Guy, go ahead and pursue it for one more minute, and then we have to let it go.
Yeah, well, the other aspect of the presentations, which is very positive and it's very classical for recent philosophy, is that when you're working with your categories, you need language. The language is a way to manipulate your categories so that you can do some reasoning on it, you can decide on it, you can have aims and so on. You could just, and that is shown in your presentation. The difficulty or the hypothesis is maybe it's not symbolic, maybe it's a vectorial way to go. But that's the question that's raised by your presentation, and I find very fascinating.
Let me give two responses to that. One is when children are learning, when they're interacting with the world, like a 5-month-old can't speak yet. There's some degree of understanding, but the depth of linguistic knowledge isn't there. But they still have categories, right? They know that certain things they can eat, certain things they can grab, and those categories come with their interaction with the world through affordances, Gibsonian affordances. So there is a degree, you can still manipulate categories without language, but the nice thing about language is now I can manipulate them outside of the time and space where I've learned from them. And I think our goal is to get there with this model. It's not obvious when you look at these figures, which are very complex, that we will be able at some point to do both the grounding and the more abstract manipulation of these at the language level. But if you have enough, for example, if the object has categorized an elephant neatly from other categories, and it sees another elephant somewhere else, and it recognizes that's the same category as this, to me, it doesn't matter if it does that at the low-level categorical level or if it does that at the linguistic level. Because if someone comes along and says that's an elephant, and the model learns, okay, I'm going to ground the word elephant with all of these vectors that I have in this category to give it nice training data. Then if someone goes along and says, then it has this elephant categorizer in its vocabulary, and it can use that for objects it hasn't experienced before in a completely different space. So it can look at a new object and think and apply it to the elephant classifier and ask, is this an elephant or not? And the elephant classifier can say yes or no. If it's vague, then the human can say, no, that's actually an elephant, and that gets folded into the category. So I think at a technical level it's possible, but there's still a lot of open questions there.
Thank you very much.
That's excellent. I want to thank you too. Stand by, because this is going to continue, and it's going to continue in the summer, and we'll get in touch with you again for the summer series.
Great.
Thank you
Yeah,
so much.
these have been great. Thank you very much.